All right. Cheers. Thank you, folks. Thank you to the moderators and the video crew, and thank you all for coming. Welcome to the session, Better Data Exploration and Visualization with Elasticsearch and Kibana. So to get started, how many of you know what Elasticsearch is? Can you raise your hands, please? Ooh, not very many. Okay. How many of you know what a Jupyter notebook is? Ah, okay. I don't have to introduce that then. Um, okay, so my name is Emanuil, and I work for Elastic. Elastic is the company behind the Elastic Stack, which is a suite of tools that have quite a lot of varied uses, but recently we've been asking ourselves whether they can be also useful to data scientists and in what ways they can be useful. So the thing about the Elastic Stack, and these are the main open source projects in the stack: Elasticsearch, Kibana, Beats, Logstash, and more recently perhaps APM as well. So the thing about it is that a lot of data scientists and data platform engineers end up having data in the first bit over there in Elasticsearch. And then because we've been focused on other use cases historically, which I'll talk about, they kind of end up in this limbo of having data in there, but not really knowing what to do with it, not really knowing what they could do with it. Using our tooling. And so what ends up happening is people just siphon the data away from the data store as quickly as possible into a Jupyter notebook where they can use Matplotlib, they can use Python, Pandas, and so on to analyze it. And that's like, there's nothing wrong with that at all. Like, actually Elasticsearch and Kibana, which these two here we're going to talk about now, are not a replacement for the tooling that you already know. They are not replacement for Jupyter or for Python or for Matplotlib, Pandas, and NumPy. However, if you already have data in there, you might as well know a little bit about the capabilities of Kibana in particular, which is the graphical user interface to the data store. Um, because if you already have it in there and you're only doing prototyping and exploration, then there is no point in spending all of that time and difficulty getting it out of there into a notebook. And so, and furthermore, there are some other advantages to Elasticsearch itself, that it can do things that a notebook can't do. Right, so since many of you said that you don't even know what those things are, let's start there. So Elasticsearch is an open source distributed data store. So it's essentially something that you throw JSON at. It's a NoSQL data store, kind of a little bit similar to a database, but very different underneath. It's based on Apache Lucene, a search project, an indexing engine that's over 20 years old, also open source. So the thing about Elasticsearch is it's used a lot in web monitoring, for example, and in business analytics. So you can throw a lot of data at it. For example, every single request made to a website or every single line of logs written by a web application and by the other components. And it can handle that relatively easily. It can allow you to do a full text search over that, or be used as a time series database to plot graphs, do date histograms, and do other kinds of analysis like that. So its main advantage there is its ability to, and I'm aware that it's a cliche to say this, but to scale horizontally, and I will clarify what I mean, is that every data store has the ability to scale horizontally. Like MySQL 10, 15 years ago had the ability to scale horizontally via read replicas. Like, I've set those up, I know. But in my experience as a sysadmin, Elasticsearch is vastly easier to scale horizontally than the other data stores that I have experience with. It's been designed like that from the ground up. Its actual search and text search abilities have nothing to, well, Elasticsearch itself doesn't enhance those that much. That's mostly down to Lucene, the underlying open source project. But all of the Elasticsearch project has to do with gluing different instances of Lucene together. So it has to do with this whole distributed layer and with dealing with incoming data quickly and efficiently. The main mechanism that it does that is by sharding incoming data. So in Elasticsearch, instead of a table, like you might be used to, you'll have an index, and that's how the data is stored. And each index can be broken up into pieces, shards. So for example, an index could have 100 shards, and if you have 20 servers, Elasticsearch will take care of distributing those pieces. And you can have replicas, so you can suddenly have 200 shards and 300, and however many you like. And that essentially enables you to easily scale your compute workload. Say, for example, that you found that your servers were being overwhelmed by the queries that you were sending or by the analysis that you were doing. You can easily add another 20 computers and order it to create a replica of the data set. So now you have 200 shards over 40 computers. So that, and it take care of rebalancing that. That's the main reason why it's been used a lot, and mostly by sysadmin people, by ops people, operations. Okay, so then Kibana is the graphical user interface for that. Now, Beats and Logstash, we're not going to talk about very much here. They're open source projects to help you siphon data from, essentially, if you're monitoring a website for metrics like CPU, disk I/O, so on and logs and so on and so forth, putting them in. So you already know what Jupyter notebooks are, so I'm not going to dwell much on that, but obviously that's some of the typical tools that data scientists use. So one advantage, so I mentioned, right, that you can use, like I'm thinking this of two ways you could use Elasticsearch and Kibana, and it's all this tooling is free, by the way. As data scientists, so I thought of two ways, right? So as I mentioned, it was in the phase of exploring a data set, and that it could do some things that maybe you can't do in a notebook. And that one has to do with scale. And this is typically the question I ask when I'm talking to one data scientist and we're having a conversation, usually at a PyData meetup. Let's take any one of your notebooks and let's ask them the question, how big is your notebook? And it's like, well, that's a weird question, right? How big is it? It's 300 cells. You know, how big is that? Well, it is an abstract question, and it's similar to, you know, how long is a piece of string? There is no answer to that. It's an abstract question. So, is it the megabytes that the data set in the notebook, or is it the amount in memory, or like what is it? But just as like how long is a piece of string, we do know that it has finite length. So there are limits that you will hit when you're using a notebook. In particular, you'll hit the limit of your own PC. So a notebook, or the code in a notebook, can't be easily distributed as a workload to other machines. There are, of course, projects like Spark, HDFS, which allow you to do similar analysis on like really well-distributed really well-distributed scale, and you can productize models that you built up in a notebook, and you can deploy them and using like something like Kubernetes and containers, and using projects which allow you to productize Python models and put them in production. But these are it's not a very easy way of doing that. It's quite involved, and likely as a data scientist, if many of you are data scientists, you won't even be able to necessarily do that by yourself. Like you'll be working with a whole team of people, so it'll be data platform engineering or data engineers that take care of that scaling out. So here is where I think Elasticsearch can be helpful, so long as your analysis fits within what it can do. And I'll show you in a bit what it can do. All right, so sorry, I keep getting shocked by the chassis on my PC every time I touch it. Right, so yes, where was I? Right, yes. Right, so let's go ahead and actually see, because I'm just thinking what would be the easiest way to show you, because so far it's been very abstract, and I'm talking about scaling, and I'm talking about the limitations of a notebook, but Let's actually see some of Kibana in action on a data set. All right, very good. Okay. Non-minimizable windows. Sometimes I'll never understand iOS. Okay, so first off, actually, before we dive into the graphical part and start thinking about how you might want to use that, how are we doing for time? Okay, 15 minutes, great. Just to show you what Elasticsearch itself actually is, like in case you have data stored in there and you have used it using just some tooling or using a Jupyter notebook only, this is what it is. This is all that it is. So there is no other interface to, well, that's the graphical interface, but even it talks over the API. So that's just a pure JSON data store. So you would, in Elasticsearch, you would do things, well, you can't really see the address bar, can you? Let's see if I got a better way of showing you. Okay. So this is the exact same thing. So the way that you would search for something in Elasticsearch is like this. These are the types of queries that you would build. So this here is an index, in this case vil. Yeah, I think I'm pronouncing it right. It's in French because the example I've stolen from a colleague who's French. So you have this kind of thing. You have a query. So this is probably reminiscent of a SQL query for you, because I assume most people have. Who here has used a SQL query ever? Yes, that vast majority. Excellent. Okay. So now I want to give you the reason I'm showing you this. I know it doesn't feel super relevant right now, but the reason I'm showing you this is I actually want you to walk away as a data scientist with some understanding of what Elasticsearch itself is, because that'll give you an understanding of what data sets you might be able to uniquely use it in. And I think it's one of its most powerful uses is actually textual analysis. And this is also one of the use cases where using a Jupyter notebook is quite hard. There are, of course, toolkits. I mean, you can do NLP, and you can do various indexing and tokenization of text and analysis on that. But actually, if you could pour terabytes of text into a few nodes that run Elasticsearch that you can set up yourself, you can even link some laptops together if you wanted to, I think that you would find its API and its queries easier to use than some of the tooling available in Python for text analysis. I'm going to show you I'm going to walk quickly through a basic example of textual analysis, and then we'll look at the pretty dashboards. So first off, clear off the data that we do have. So I just deleted the vil index. Now we're putting in a sentence in there. So as you can see here, this creates a specific document. It also creates the index as I go. So the index was just destroyed completely. But by attempting to create one document, it creates the index also. And the message is ici c'est Cergy. So this is Cergy, or Cergy. It's a town in France. Okay, so here you can notice something interesting here that it might be useful to walk away with. It created the index without asking me for a schema. So it's not quite schemaless because now it thinks that message is a string. So it will expect message to be a string in any subsequent document. The same will be true if it were a number or if it were a date. So if the first document that it sees has a field like date of birth, and that's a date, and then you try to give it the string ABCD, then you will encounter an error. So it is not schema-less, but it will accept any shape of data to begin with. And which is useful if you're just uploading data from a Jupyter notebook. That's useful to know. Okay, so we're just now retrieving that specific document. So this is the ID of the document, Sergi. You can also create documents without giving it specific ID. You could do updates to them and so on. And we can execute a search. Now, you'll notice the search returned no results. And this is actually exactly the point I want to make. So about Elasticsearch. We're going to try, and okay, wait, let me show you again. Original data, right? Sergi is written with capital C. I'm looking this some query, and those of you who know Elasticsearch might already notice the problem. We've got the town with capital C, we've got the town with capital C, shouldn't be a problem, and yet we get nothing in return. Right. And if we look for it with lowercase c, it works. Are there any Elasticsearch users in the room actually? So does anybody actually know why this is happening? No? Anybody want to venture a guess? If any of you are familiar with search technology in general or indexing? No. Okay, cool. Right, I'll just tell you in that case. Right, so there is, here's an example which will work, hopefully. Yes. So capital C again, but this time it worked. And here, only the lowercase c worked. Now, I know we're here for other things, so I'll skip over this part more quickly. I'll tell you the difference. The difference is that the query type is different. One is a term, one is a match query. And this is the important thing to understand about Elasticsearch, and something which you can use to your own advantage when you're working with real textual data. So the way that Elasticsearch works is you receive data, right? You got a data stream pouring into Elasticsearch on the one side, and on the other side you have queries that are coming in, and it's expected to return data. Now, as the data is coming in, it goes through a process called analysis. As part of analysis, there is normalization, tokenization, and other things. So tokenization, for example, would be breaking up this sentence by, say, white space. So it'll be in this, if it were only by white space, there would be 3 tokens: EC, set, and Sergi. Then you have the process of normalization. Now, in order to find something, you need to have kind of a baseline to search for. And so the analyzed version, with the default analyzer, lowercase is everything, right? But this is only part of the mystery, since obviously one query, the match query, returned the result with a capital C, and the term query only returned the result with a lowercase c. Okay, so as the data is coming in, it's normalized, lowercase, analyzed, etc. And this process is particularly powerful. Like here, you can have your own custom analyzers. You can have analyzers for different languages. So for example, for German, where you have compound nouns, and where you have other things, there's an analyzer for that. Recently, an analyzer for Korean was written. So they're very powerful plugins which can really get into what's special about the specific language. So if you have pure text data, it is much easier to use this than to try to replicate the entire process of analysis in Python. You can, the same tooling exists as it does in Java, which this is written in, but you have to do it yourself rather than use an open source API to do it for you. But anyway, why did this example work out like this? Well, data comes in, analyzed, normalized, tokenized. On the one side, it's lowercase in this process. Then on the other side, the query comes in. It's the word Sergi, capital C. The query, by default, with using at least most types of queries, is also analyzed. So that the same process is applied to both the data coming in and the data coming out. When a query is issued. So Sergi is lowercase in the query, then lowercase here from the analysis process during indexing, lowercase here from the analysis process during querying, and they match. All right. But so this is where when you use a term, this is why when you use a term query, it works, because you get the lowercase. So a term query is non-analyzed. A term query, whatever you give it, it doesn't go through this process. So imagine, like I guess most of you know about idempotency and about symmetrical data processing. If you process the data as it's coming in and then you don't process it in the other direction, then obviously it's going to fail. And this is what's happening here. But the term query is thus useful as it allows you to search for something where you know the end result of the analysis process. This is particularly useful, again, if you've done NLP or something like that. You would have to perform this analysis yourself. But you also can just use data in its original form. So in this case, capital C. There are also tools that allow you to do that, because then the algorithm is applied to both sides. So right. I'll move on from that in the interests of time. But the reason I showed you that is because I think it's something, part of the session, the point is for you to learn a little bit about Elasticsearch. And that really shows one of its both core strengths and also a possible frustration that you might have as you start using it. Okay, so let's get on to some actual aggregations and things that you might be more familiar with. So I've uploaded 10,000 documents which have to do with personal data. So there'll be some addresses, year of birth, and, I think number of children, gender, and so on. And I've just issued an aggregation request. Okay, so here we see we want all the records. We don't want any of the hits. So we want the query to cover everything, but we don't want any of the results. Okay, right. Then we want to look at the analysis that this allows us to produce. And we want it by year, so we want it grouped by year, and we want a date histogram. So if you've got a date stamp field, then we want that to be further broken down by gender and to be further broken down by the number of children. And here's what we get. And I promise you I will show you the graphical interface for this, which will be a lot more fun. But I think it's important to see how it actually works. So first off, we get by year, and we get individual buckets. So this will be 1940 to 1941 in this case. And Elasticsearch looks at the data and looks at the bounds for you, and detects the boundaries of the data set and starts the buckets from there. So in this case, there were 146 women, and on average, born in that year, and on average, they had this many kids, and on average, 143 men, and so on. Okay, now that you've seen that part, let's have a look. This is the underlying data set and how the thing works. Let's have a look at some more interesting tooling. So if we decide to look at the last 80 years of the data set, this is what we see. So we immediately, it's a good tool for kind of immediate exploration, and you can also see individual records. Now, I'm just wondering what exactly would be most useful to show to you. You can require summaries, or you can extract summaries like this. So it's a relatively easy way, and you could do this with head. Like so far, I haven't shown anything that unique. You could do this with a head in pandas, but this is how you do it in Kibana and Elasticsearch. However, you could also relatively easily filter. So for example, let's say that I was only interested in people where we have a relative score of their interest in music. I'd click filter for field present. And now we've only got 5,000 out of 20,000 records. And so here we are. So, and possibly not that exciting, but it's important to know how you would navigate this kind of thing at all. Right, so now let's get into the meat of it. What can you do then? As I said, we've got two ways. One, you could scale, and so if your data doesn't fit into a notebook, for example, you might fit 10,000 records, 100,000 records, even a million, depending, of course, on the size of the object. How long is a piece of string? But if you wanted to fit information like this about each inhabitant of the planet, then you would be hard-pressed to run it, even on a modern MacBook or Lenovo workstation. You would need something more. And then this is where like this kind of thing comes in, because Kibana, the graphical interface, will work just as well with 1 billion records as it will with 1 million records. So at least when it comes to summarizing them. Okay, so I'll first show you the most exploratory type of visualization you can do, and that's a time series visual builder. So immediately we start off with just a count of documents, and this is when people were born. Okay, maybe not that interesting. Now we could group that. Let's try a gender grouping. And now we can see in each year how many people were born by that gender. Or we could try country. It updates immediately. So you see Germany, England, France, and so on. And this is again number of people born in each one. So this is your most basic tool. This is like the Swiss Army knife. What you can do is create much better visualizations than that. So if I do an area graph, and I guess I know that you can do these things with matplotlib. My point is that you can do this over much larger data sets, and you could do it more quickly. At least I think so, once your data is, if your data already is in Elasticsearch. Okay, so I got the count of documents. Yeah, doesn't look like much at the moment. So what do we want? We want a terms aggregation, but what do we want it by? Let's say we want it by country to begin with. There we go, that's a little better. Okay, you got Germany, England, Italy, and France. Sure, well, not that interesting. You can do sub-aggregations, and that's something that's a little bit harder. So, for example, you could split this chart. This would probably be appropriate. By gender. So otherwise it's going to start looking quite difficult to manage. Okay, and then you can split the series. After that, you can basically split series as many times as you like. So what we have so far, we have country, and let's say average number of children. So that will be a range aggregation. Actually, in a range aggregation, you have to define it yourself, so I'm just going to do a histogram, because I don't know what the bounds are. The point is I'm exploring the data set. Like that. I've just hidden what I've done. Right, there we go. And here's the average number of kids. So if you have 4 kids, then you're in here, and so on and so forth. And you could do pie charts, and you can do many things, as you saw in here. Now, one of the interesting things that I would like to show you is a coordinate map, and how to create one. So it automatically tells you which fields have the suitable types of data, so you don't have to wonder about that. And here you go. So at the moment, it's just showing a count of documents. So it's how many people were born in those spots. And as you zoom in, this is using OpenStreetMap, by the way. As you zoom in, you can visualize it. It breaks down the heat map bubbles basically further and further. Now, what if instead of count of documents, we did an average? And since we've been using this example, I don't want to confuse you any further, let's do average number of children. Okay, so you can see here the bounds of the data set. And then we can zoom in further. Now, let's say that I live in London. South of London, we wanted to limit the data to only those that part of the data set. This is how we would do that. And there you go. So now we're looking at a very particularly filtered visualization to just that part of the data set. Now, what we can do is save it. I'll just call it my map 2, because why not? And so as you can expect, I guess, from in any similar project, it remembers exactly where you were. It remembers your zoom level, the place on the tile, and so on and so forth. So you can easily share that with people. You can also embed it. The embeddings are only iframes at the moment, but you should know that that is possible if you wanted to embed it in a web page, which I imagine would be what most of you would want to do. Now, you can also dashboard this. So if you wanted to give your business a false sense of control over reality by showing it pretty graphs all together, and you can certainly do that. Or of course, if you think hard about how to make a dashboard useful, because a dashboard by itself that isn't always that useful. But if you think hard about how to make a dashboard useful, you could actually give your business some control over what happens to it by enabling correct reports for your execs and for your colleagues to derive the right ideas from. There's a pie chart in here that I've defined before. There you go. And you can move these around and save these and so on and so forth. So for example, I'll show you some more advanced dashboards. This was just to show you the process, but you can create lots of different things. You can create text to explain something. So you can actually do, if you wanted to do this up as a story, because I'm aware that Jupyter notebooks are often used to display a whole analysis as a story, right? Starting from an introduction, starting from source data, so you can see each line as the source data is loaded. You would be able to tell a similar story here. Not the loading part, but like text to explain what is coming, and then visualizations to explain whatever it is that you're aiming for. You can do all sorts of maps and other things with it. So this in particular, this is flights data. It's not live. Couldn't risk that. Pardon. But as you can see, you can do heat maps, and you do all sorts of stuff, and the mapping information is free, so you can use that. You just load up your data set and use it. The other one I like is the world's earthquakes, mostly because of the heat map. I think it's fascinating that you can just pour those in and get a map like this. Another advantage of using the stack for the Elastic Stack for this kind of application is that you can set this stuff to automatically update itself. So for example, if you put this up on a monitor or on a web page, as you pour data into Elasticsearch, the thing can be set to requery. And I believe we're working on a kiosk mode as well if this is the kind of thing that you would want to do. So there's I guess most people, the way I've heard most people use this type of functionality is just for putting together reports for their business, like for the business stakeholders that you have. Now there's other interesting things you can do. I will warn you, this is the first thing I'm showing you that is commercial, so it is paid, but I'm showing it to you because I think it's interesting in its application. And you can, of course, also do this totally using Python. You would just have to know how, I guess. Using scikit-learn in this case probably be most appropriate. So this is a machine learning module. So here you have, over there you have top influencers. So I have not, this is completely unlabeled. This is completely unsupervised. What it's looking for is an anomaly. So this is anomaly detection, which could be useful for a lot of uses in data science. It has decided, I haven't told it, it has decided that user.name and transaction.name here are the most important things that you should care about. So it's inferred that from the data. It uses a number of algorithms to do that. Of course, I'm sure somewhere inside it also uses linear regression, like we all do. All ML is ultimately linear regression somewhere. But this is the kind of thing, I guess, that it's capable of doing. probably get best results after at least 2 weeks of data. In this case, it's website performance data, but you could use any kind of data to try to detect anomalies. And for the moment, it works best with time series data. So this would be only anomalies in time series. And that's basically what we're looking at. So you got more than 100 times higher. So you got like, it's detected that typically this is the number, the feature, that might be interesting. And then actually this feature has now over 100 times more. So you should maybe look at this. So this is just a way of trying to look into your data set and trying to gauge what might be important. Now, of course, if you have a lot longer to spend on a data set, you will want to be exploring those kinds of relationships yourself. But if you have a lot of them to go through, and they are in Elasticsearch, or you want to put a portion of them there, then this is how you do that. Now, let me show you one last thing, because I also want to ask you some things. Yes. So for who here uses Python? Okay, about half the room. R? Okay, well, you're the same people. You're just multilingual. Very well. So at the moment, this is the kind of thing that you would have to do in order to upload data from a notebook into Elasticsearch. So there is an official Python Elasticsearch client, and it's also Ruby and many others. Our support is not so good, but Python is very good. So you would, as the scientist, you're probably not particularly excited by these lines. They will look to you like the glue required to use many other data stores like MySQL and Postgres, and indeed it's no different to that. You essentially create an iterator loop over your data set, but there are, there's reasonably well understood ways that you can do this. So you will not have a lot of trouble with it, is my point. And likewise, if you're trying to pull data from Elasticsearch into Pandas. Right. I just wanted to mention that. Now, the the point of showing you this stuff is that in Elastic, we are trying to think of how do we move on from, well, how do we move on to different use cases? Like, where are people already using us? And I know, at least in London and financial institutions, that people use Elasticsearch a lot. Like, it's for stuff like this. For example, we've got Uber using us, Tinder is using us. That's a different kind of search. Uber is using us for geo search. Big retailers are using us. And so then on the back end, the data collected, like business analytics. For example, if I was a big retailer, you would have, okay, well, how, like a number of sales, for example, and it might break them down per store, and that's data that's coming in relatively real time to you. But you already have it in Elasticsearch, so, and this is all like the web team, right? It's nothing to do with data science. But then they want analysis. Does cold weather influence buying patterns? Well, the data is already in Elasticsearch. So guess what my friends are asked to do? They're asked to use Elasticsearch in order to answer questions like, does cold weather correlate? And if they have a whole lot of records, it becomes unmanageable in a notebook. So this is what we are thinking of as a tooling vendor. We are already being used, like, we're already focused on a ton of other use cases. As you can see, a search is a very versatile tool in general, so that makes sense. But how could we become more useful to data science? And so far, I have come up with these things. You could build dashboards, reports, possibly the unsupervised learning thing, although that's commercial, so maybe you would be a bigger company. You can also get that for like small data sets quite cheaply, but it's still paid. And I know data science is used to free tooling. And then finally, analytics, so correlating business metrics with other numbers. So That's where I'd want to talk to you, and I'd want to understand. So come to the AMA corner and please talk to me. I'd want to understand what your particular problems are. Like, are there limitations that you're hitting in your tooling right now? Like when you do, for example, predictive models, where do you hit the edge cases? Like, do you hit edge cases in terms of the size of data sets? Is scale a problem? Is the ease of deploying a machine learning model a problem? Or do you not even care about machine learning? You know, do you just care about correlating some numbers together and putting together some graphs for your business stakeholders? Like, it, what exactly what can we do to help you more? Like the tooling is already free and the vast majority of it's also open source. So I think it makes sense that where you that it makes sense that you would use it in cases where you don't need the full flexibility and power of a Jupyter notebook or where you need larger scale. So yeah. That's kind of an intro to Elasticsearch and Kibana, and yeah, that's it. Thank you very much. Do we have any time to ask some questions?
Yeah. Thank you very much, Emanuil.